Now, to illustrate how effective hydrogen bonding is for water, especially to keep it in the liquid state, I'm going to do a little demonstration here where I've got two temperature probes, okay? And on one of the probes, I've got filter paper wrapped around both, but on one probe I'm going to put acetone, okay? And acetone's chemical structure looks like this. Okay, that's an acetone molecule, and it weighs 58 atomic mass units. Now remember, water, it's shaped like this, and it weighs 18 atomic mass units. So water's a lot lighter, okay, than acetone. And water should evaporate. It should go from the liquid to the gas state a lot easier, a lot quicker than acetone should, because acetone weighs so much more. All right, but let's see how it really happens here. So I've got some acetone in a little squirt bottle, and I've got some water in a little squirt bottle. And what I'm going to do is I'm going to wet that filter paper down from one of the probes with acetone so that it's saturated with it. And the other one with water, so that it's saturated with the water. Okay, and then I'm going to hit collect. There we go. Alright. Now the red line here, erase this so you can see it. Temperature 1, the red line, that's my acetone. The blue line is my water. Now remember, acetone weighed 58 atomic mass units. Water weighs 18 atomic mass units. So you would think the water would evaporate much more easily, much more readily than the acetone. But as you can see by the temperature change, and remember, as something evaporates, it cools. It has a cooling effect. So the faster it's evaporating, the more drastic of a temperature change you're going to see. All right? So what we're seeing here, the acetone is evaporating very rapidly. And you can test this yourself if you got some fingernail polish remover, put a drop on your desk, watch it, it'll evaporate very quickly. Water, a lot slower. Okay, the water is evaporating, it's coming down, it's cooling off. That's why when you run, you start sweating, it evaporates the water out of your body. It has a cooling effect to cool you down until your body maintains homeostasis, stays around 37 degrees Celsius by either closing your pores and causing you to shiver, to warm up, causing your muscles to shiver, or if you're hot, opening your pores and allowing you to sweat, because as that water evaporates, as it goes from the liquid to the gas state, those hydrogen bonds break, okay, that cools you down. And you can see that cooling effect here of water. But look at acetone, okay? So even though it weighs 58 atomic mass units, it's evaporating very quickly compared to the water. Okay? Why is that? If water weighs a lot less, one water molecule weighs 18 atomic mass units, and acetone weighs 58, why is the acetone going from the liquid, because I started out as liquid acetone, just in a little bottle here, and I put it on my filter paper, to the gas phase, so the acetone went from liquid to gas, so much easier than the water? Well, the answer is hydrogen bonding. Okay? The acetone molecules don't hydrogen bond together, so they'll just go off into vapor a lot more easily. They're not attracted to each other. They don't have that surface tension, okay, like the water does. The water, because of its hydrogen bonding, one water molecule being attracted to another water molecule, to another, to another, to another, for one of them to break free from the surface of that filter paper and go off into the gas state, you have to break that hydrogen bond, and that's harder to do. Okay, so I have to break this bond, that intermolecular bond, to let the water go. So even though water weighs less than acetone, it only weighs 18 atomic mass units, it's still hydrogen bonded to all the liquid below it. So at the surface, those water molecules that are evaporating off first, they're doing it very slowly because of hydrogen bonding. Whereas acetone, very quickly, because there is no hydrogen bonding there. Okay, remember that structure of acetone? It was because of the shape of it, the structure of it, you don't have that charge, you don't have that polarity, you don't have that hydrogen bonding. So one acetone molecule isn't hydrogen bonded to the others. So it'll leave at the surface, where the surface of the liquid is, the acetone, it will evaporate very quickly, very readily. And that's what that diagram illustrates. Okay, to sum all that up, the properties of water are unique. And life wouldn't exist on this planet if it weren't for those unique properties. Okay? Water has a very low vapor pressure because of that hydrogen bonding. Vapor pressure is the pressure for water to go from a liquid to a vapor. Okay? The tendency for a molecule to leave the liquid state and form a vapor is its vapor pressure. Water has a low vapor pressure because it has a low tendency to evaporate because of hydrogen bonding. Okay? Surface tension, where water molecules are attracted to each other, and if you put them in a non-polar environment like my wax paper, it beads up, the water does, because it pulls in, it's attracted to itself, but it's not attracted to that non-polar wax. And a sphere is the shape that has the least amount of surface area, and that's why it pulls up like that. Polarity, the ability to dissolve substances, water has, because the shape of the water molecule and the separation of charges makes it a universal solvent. All these properties are unique to water. The density, as water goes from the liquid to the solid state, forms that lattice formation, spreads out and becomes less dense so that it floats, okay, on top of liquid water. That's unique to water because most solutions, most substances, when they go from the liquid to the solid state, become more dense. Okay, but water becomes less dense. All of those properties of water make life possible on this planet, and are unique to water because of its structure, because of its polarity, because of its hydrogen bonding. And that's really the crux of chapter 17.